Yeah, not only special and general relativity, but it's also going to cover the whole historical timeline, starting from Kepler and then getting into Newtonian dynamics of the solar system, and then what had to happen to keep the idea that the Earth is in motion around the sun alive. And, that's where we get into the special and general theories. And so we're going to pay particular attention to those towards the end. But yeah, we're going to go through the whole narrative. So this is How Math Met Reality, the extended cut, and the battle for your mind, right? All right, so here's the little intro video I made. So how math became, actually, 1 second. Full screen. All right, there we go. So how math became reality. All right, so we got Kepler, Newton, and Einstein with all these theories in conjunction with each other where you can derive one from the other to describe the motion of the heavenly bodies. We're going to get into the specifics of what exactly all that means. And in the finalized form in modern physics, we have the special theory, which says C plus or minus V equals C. And we have the general theory that says C plus or minus V does not equal C. So we have two theories here that say different things. All right. And to get us started off with the story here, we have to understand some important concepts in physics. So this is kinematics and dynamics. So to get into kinematics and what kinematics is, let me see, is that still, yep, okay, cool, perfect. All right, so to get into kinematics and dynamics, these are two important concepts in physics. The kinematics part breaks down motion, and all it does is you make measurements, and then you make predictions of like where things are going to be based on how fast they're moving, things like that. You're not concerned with the why they're moving or anything like that. It's just, it moved within this time frame. How fast was it? Where is it at now? Where would it be if it continued to move at this velocity, et cetera, right? All right, and then you'll see equations for kinematics that usually look exactly like that. So you got velocities, you got acceleration and time, and then you could break those down to different derivatives of time, and you could figure out accelerations within how long based off of how long something's moving and how fast it is, how fast it was moving. So to give an analogy here, it would be like gravity, or I'm sorry, it would be like dropping a ball from a tall building. You're not concerned with why it's falling, right? Just that it's falling, and then you could use kinematics to tell anything about that falling ball. How fast it's going to hit the ground, how fast it's going at this 2 seconds into the flight versus 4 seconds, etc. So you can break everything down like that with kinematics. Now you're not interested in the why, just what's happening. So to get into dynamics, the secondary part of physics, that would be making predictions of future motion based off of the why, adding actual forces to explain to make the predictions of the motion, right? So in this analogy, think about it like, let's say you're watching NASCAR, right? And you're watching the car go around the track, how fast the car goes, how many laps it's doing, all that stuff. And you could make predictions of, where the car is going to be based off of that, right? Now, the dynamics would be like breaking down the tire friction on the asphalt, the fuel, oil, all that kind of stuff, how much it's expending, all that, like literally all the intricacies of the system that makes the car move. You're going to apply that and then figure out how far the car would move with X amount of fuel or something like that. So that's kind of how that's the difference in the two systems, right? One makes predictions based off of nothing, just off of empirical observation, and the other one deals with actual forces. Okay, so now we're going to get into sky, what's going on in the sky. So we're told that the heliocentric model is based off of ellipses, so we're going to understand what an ellipse is. So here we have S prime and S. These are the foci points of an ellipse, and then at one of these points, Kepler says that the sun will be there, and then the orbital bodies the bodies that orbit it will go around it. So when you're going around an ellipse, you have a perihelion and an aphelion. So when you're perihelion, you're on this side coming around the sun, and when you're aphelion, you're on this side. All right, and let's see. So focal points, okay, cool. Okay, so now we know what the elliptical orbits are. We can get into the laws that describe their motion, right? Because this was what was first put forward to describe the motion of the heavenly bodies. And with no concern for an actual dynamic mechanism, Kepler just said that the reason that all this motion was going on was that the sun was singing a heavenly song, and the acoustic vibration from that was causing pressure mediation in the sky, and the orbital and the bodies were responding to that pressure mediation to the sun singing its heavenly song. Now that's cool. Now a lot of people are like, that doesn't help us with anything. But what is important, or the important part of Kepler's theories was the math relationship for the bodies to give them orbits and actually to put distances to their actual orbits, right? Because when you're watching something move in the sky, you can't tell how far away it is. You can't tell anything like how big it is. It's just based off an angular size. So you don't really have a reference to gauge an actual distance. Now these, what Kepler applied to the equations gives them gives them distances for everything. So the first law we have is all orbits are ellipses. So instead of circles, they're ellipses now. And then the second law is that based off of where the planet is in its orbit, so if it's aphelion or perihelion, it's going to be moving faster or slower. So that's the second law. And then the third law is that the square of the orbital period is directly proportional to the cube of the semi-major axis, right? So what that means is, so the semi-major axis, by the way, if you break an ellipse in half like this, long ways, the major axis will be here, and the semi-major axis will be vertical. All right, so, and this will be proportional to the major axis. Sorry about that. To the semi-major axis. Okay. And then, so we got these laws of motion, and then now we're going to look at what happened when Newton applied dynamics to it. So we'll go over that real quick. Need to switch scenes. Cool. Okay, so cool. Don't have it up already. 1 second. Cool. Nope, that's the wrong one. 1 second. Which one am I getting here? There we go. Okay, sorry about that. So here we are with the equations that Newton put forward. So we have Kepler's laws that give you a orbital radius. And basically what Kepler did was he converted velocity into 4 pi r, which allows them to translate how fast it's moving across the sky based off its periodicity into an orbital radius. So with that, Newton applies Fc equals Fg, right? So he's saying that centripetal force is equal to gravitation. And then with that, he gives the equation here, Fg equals 2 gm over 4 pi r squared, and times the periodicity squared equals the semi-major axis cubed, right? For the distances. So we're saying, okay, all this is proportional. And then now we've included dynamic forces, right? So Newton proposing mass attracting mass as the dynamic force. These bodies are going to move in relation to each other based off of their mass. So again, what we did here is we converted the v squared to 4 pi r squared, and we take this m, this cancels out, so it's not relevant in the equation, and then we just have our established constants, this big G and this big M, over 4 pi r squared times the periodicity squared is equal to the distance of the cube of the semi-major axis, which gives them their orbital distance. 1 second. So to put that in perspective, right? We have Earth. They did the Cavendish experiment. They say based off of that relationship, they came up with these constants, G and M, right? So we watch the sun move in the sky over the course of a year. So there's our periodicity. And then the sun has a little m right here. We don't know this, right? It's not relevant. It'll cancel out, but we can backwards derive it later after we get this part of the equation done. So they've got their periodicity. Now, when they apply that, that's where they get their distances for everything. Everything scales off of that relationship. Send it back. Everything scales off of that relationship. So that's where they get their 93 million miles for Earth. That's the astronomical unit, and how they derived how far away the sun is from the Earth is based off of that, based off of these equations and watching the periodicity. All right. So now once they have that established, right, they can backwards derive the mass for the sun. Then they got the gravitational influence, and then they can go, okay, well, the periodicity for Mercury, the periodicity for Mars, Jupiter, Neptune, Uranus, Saturn, all these planets, right? Same thing. And then it'll be in relation to the sun. And that's where, and then from that, they get this nice clean, orbital, orbital graph here that extends, like it looks like it's linear, right? But these distances, like as it gets further apart with the scaling on that, these distances are huge, but this gives them that nice linear looking way that they derive their distances. Okay. So that is Kepler's Newton, right? And with Newton comes along, or with this explanation of the sky, what comes along with that is a mandatory 30 kilometers a second velocity, right? So this mass attracting mass force is going to produce a 30 kilometers a second velocity to complete that orbital period, right? So in order for the Earth to go over, to complete this periodicity squared and all this stuff, has to be moving at 30 kilometers a second. So we'll pick back up on the from there on the regular presentation now that we know what they're doing with the sky and the equations. 1 second. So monitor and then back to browser. Cool. All right. Cool. Okay. So to make a definitive test of what's moving, is it the sky or is it us? A test was proposed by Airy, the Royal Society member at the time in the, what was it, 1770 something? Anyway, the idea here was that if the Earth was in motion and you had a telescope angled at 90 degrees and you were looking at starlight, you would have to correct it slightly to keep the starlight in the center of the telescope. And then if you were to fill the water with telescope, because the light slows down entering the refractive medium, you would have to tilt the telescope further to make that, to, you know, offset that velocity change if the Earth is in motion. If the Earth's not in motion, then you will not have to do any additional corrections and you're pretty much good to go. And that the implication is that the Earth is stationary. So this is known as Airy's failure. So we got the Earth 30 kilometers a second, empty telescope. It's just off of 90 degrees, keeping that starlight in the center. So they're like, I don't know, are we moving or not? Let's fill it with water and see what happens. So they fill their telescope with water and there's no correction angle necessary. Well, they had to correct it by 0.8 arc seconds, which is less than an arc second, and their predicted value was 30 arc seconds. For 6 months of the year, they were going to have to correct it by 15 arc seconds going towards the sun, and then 15 arc seconds in the opposite direction going away. And so for a total of 30 arc seconds, 1 kilometer per arc second, essentially. And they only had to correct for a fraction of that. So the implication there is that the starlight already comes in at an angle, the Earth is stationary, and because there was a slight fraction of a degree correction, fraction of a degree, the implication would be there that there's some kind of drift. So possibly an ether drift could come into play for an explanation there. So they marked this experiment down as a failure to detect the ether, even though it was a failure to detect Earth's velocity, because that's how the relationship would reflect. They wouldn't detect a jar of ether or anything like that. They would detect the confirmation of Earth's velocity would be in the correction angle. That's how it would work. Okay, so 1887, they came along with a more precise instrument to take measurements, and this is an interferometer. And what they do here is they split a light beam such that it's orthogonal to itself, so it makes like a right angle. So it's one's going up, the other one's going right to that, and it recombines. And from that, they were saying that if the light dragging against the direction of motion of the Earth would be retarded, and it would produce a fringe pattern proportional to the velocity of the Earth. And they already knew that they could measure proportional velocities with light like that, because they already did an interferometer experiment with Fazal testing the concept of Fresnel drag, where they measured the moving velocity of water through a tube using a light beam that's going through the tube such that it's going with and against the light, or with and against the flow of the water. And they measured in addition to the refractive index, right, in addition to the light slowing down, they measured a 44% proportional velocity relationship to the light going with and against the water. So a total of 88% of the velocity of the water was translated to the light. And the hypothesis of the theory was that light propagates through a material medium called the ether, and that material medium would be dragged by another material medium, essentially, as it's going through it. So as the ether is going through the water's velocity is adding to the ether, and there's Galilean velocity addition there. So the speed of light is c plus or minus the velocity of the water. So using that concept, they were like, okay, well, we can set up this interferometer such that in the direction of motion, and then one going perpendicular to the direction of motion, the one that's going perpendicular will be retarded, and we can determine, Earth's velocity that way. So the idea here was that it was going to produce a fringe proportional to Earth's velocity, and they came up with their equation to derive all that. And the reduced form of it here is 2D times v squared over v squared, and one of the v squareds is 30 kilometers a second, and the other is the bottom one. The denominator is the speed of light. So it's the ratio of the length of the apparatus times the speed of light times 30 kilometers a second over the speed of light, so that they can get their ratio for how much fringe will be displaced for a velocity of 30 kilometers a second. And they did not get the measurement that they had expected. So again, they expected 5 fringes out of this to get 30 kilometers a second to confirm the heliocentric model, like all those dynamic forces and everything that Newton put forward for the sky. This was supposed to verify that and give physical meaning to those equations. And they got just over a fringe for 5 to 6 kilometers a second, which is, devastating to the heliocentric model, because it's mandatory that it's 30 kilometers a second, because otherwise it's not going to be traveling. The Earth isn't going to be traveling fast enough to complete that orbit in time to make their model make sense. So, huge failure for them. Now they end on saying that perhaps the whole system, like the Earth and the sun and the center of and the solar system are moving together, and they need to do some more testing, but that's probably unlikely because the velocity was so low. And then he says, well, maybe we should do some extended testing throughout the year to see if they're in correspondence with the elliptical orbit where the speed changes. We should see if there's any fluctuations to correspond to that, because they weren't entirely, because the air was so great, or not the air, the gap was so great between 5 and 30 kilometers for them. They really didn't know what to make of it. So they weren't really even sure if they, what they had measured per se, right? All right. So now the jumping off point for special relativity to come in and save the day for everyone, they had to redefine physics and relative motion and put forward the kinematic framework as an actual dynamic explanation for everything. So we'll get into that now. So because this theory failed to detect Earth's orbital velocity, the spin on it was that there was no ether, and the light propagates independently of motion, and it can't be used to measure linear velocity. So we'll go over what Einstein puts forward right here in his 1905 paper. He says that light propagates at empty speed with a definite velocity of c, which is independent of the state of motion of the emitting body and also the observer, and in an inertial frame. And then he goes on to say that the introduction of the luminiferous ether will be superfluous in so much that the theory developed here will not require an absolutely stationary space provided with special properties, nor will it assign velocity vectors to an imaginary point in space where electromagnetic propagation once took place. And here he goes on to, and then we're going to read where his equations apply, right? Because if you're an inertial observer and you're in linear motion relative to something else, you're going to measure the speed of light being a constant, and you're not going to be able to use it to deduce your velocity, is what Einstein's saying, because there's no absolute space and no ether or anything like that for there to be a reference for motion to be relative to, especially linear motion. So he gives his coefficient here for all that, and then he says, okay, so my equations hold true in any closed polygonal line, and it must also hold true for a continuously curved line. So if you're closed polygonal circuit in uniform rotation, Einstein's equations should apply. And the logic for that is if you take a circle and extend it to infinity and zoom in on it, any portion of that circle is going to be pretty much linear. There's not going to be much deviation from straight. So that was the whole basis of that. And then on top of that, he introduces the concept of length contraction and time dilation. Now, these are second order effects in velocity that will cause physical shrinkage in the reference frame that it's being measured in. So if the apparatus is moving at 30 kilometers a second, there's also going to be length contraction proportional to that velocity, and it'll actually make it so that you can't measure it. And that's what they ended up going with for the explanation for Michelson-Morley. They took that 5 kilometer a second measurement, they rounded that down to a sweet 0 and said, okay, we can't use any of that, and we're just going to go from there. Length contraction, time dilation, right? So here we have the science lads trying to measure the motion of the Earth, and they can't quite do it because of length contraction and time dilation, no matter how closely they look at the measuring apparatus. So let's see, I think we're good on that. Cool, okay, yeah, so all in an attempt to keep Newtonian dynamics alive for an explanation to give a meaningful explanation of the solar system, right? Because Kepler's explanation was just kinematics, right? And they're saying that Newton is dynamics, so we're applying actual forces here to this stuff. And because they didn't have a velocity to correspond to that to confirm it, they really don't have a model to explain the motion in the sky as if with the Earth being part of that motion. Okay, so we're going to now get into the introduction to, okay, so one second here. So linear, okay, we'll touch back on special relativity at the end for interferometry. But to get into the general theory now, so in 1915, Einstein proposes the general theory, right? And this is largely based off of the correspondence principle, which states that a theory that's going to supersede another theory must also be able to explain pretty much everything the other theory did and even more, right? Otherwise, what are you doing? So it's based off of that. And then the equivalence principle, which states that being in a gravitational field is equivalent to being in acceleration. And 1 second before we move on, and this is important because with that linear aspect of motion, they're saying that there's no absolute reference frame. Before rotation, they're saying that's an acceleration and that there is an absolute reference frame for that, for acceleration to be relative to, and we'll get to that in a second. So this theory was to swoop up acceleration, for motion, and also to extend the theory to gravitation, right? Because there was a little matter of the perihelion precession, which we'll get to in a bit, and the significance of that. But this new theory had to be put forward, and here a big, a controversy was that you couldn't derive Newtonian solutions using Einstein's field equations. And then Einstein, put a little patch update where you can take a derivative of the space-time metric. So just basically how much space-time curvature there is in a localized flat zone. And then you can take a derivative of that and make it even flatter and get Newtonian approximations for things that aren't moving at relativistic speeds or have relativistic mass. And then 1 second, we're going to transition back to the interactive slides here. And we're going to look at absolute space. Okay, so absolute space, and with the Michelson-Morley interferometer and all of that, right? So the Earth is going around the sun in an ellipse. Now this looks like a circle here, but just imagine there's a slight eccentricity to it. So this is our ellipse. The Earth's going around the sun, and they're saying that when you try to measure that, there's a gamma factor correction here. So this is the Lorentz contraction and time dilation, right? So this is your ruler and this is your time contracting with a proportional ratio to the velocity that's being experienced. And in tandem with that, they're saying that there's no absolute frame for linear motion, right? So to kind of break that down, what that would look like is if you take this circle here, and this would be where the sun's at. So at the center of the sun, the orbital, anything on this orbital circumference will be experiencing a velocity relative to the center of this, right? So relative to the center of the sun, there would be a velocity here. So we're actually going to need to change up the definition of orbits here to further explain this, because technically there should still be a velocity component here because there is an absolute reference frame in the center of this orbit, right? How could there not be? So we need to actually change orbital paths so that they're all straight lines and don't have a reference frame. So that's what a big part of general relativity theory is, right? Or that's entirely what it is, right? With the geodesics, right? So now instead of traveling along a circle to complete your orbit, you're traveling in a straight line through curvature of space-time based off of gravitational fields. So you'll have a 30-kilometer velocity, right? But you won't be able to measure it. It'll measure 0 because you're in a geodesic traveling in free fall, in a perpetual free fall around the sun, instead of an actual linear orbit. Now, they say that from our perspective, right, we see circles and we see things doing circles in the sky, but that's just from our ant view perspective on a giant ball. From a 4D perspective, what we would see is that we're actually traveling along the curvature of we're actually traveling along the curvature of space-time in a straight line. And what we're seeing is an illusion. The circle's an illusion. The truth is the straight line. Cool. All right. So that's the basis for the general theory and how they had to change the orbits to further explain everything, because in 1913, Sagnac came along with a rotating interferometer, and similarly to how they said, oh, you know, if you're in a closed polygonal circuit in uniform rotation, well, you should measure C being C. So the clockwise and counterclockwise propagation should not give a difference in the measurement, yet it does. So they had to redefine this as an acceleration, throw it in under the general theory, and invoke a direct proportional relationship to the velocity with a little temporal pocket of time dilation to explain it. But anyway, that's a little more than we need to go into. Okay, so monitor, back to that. Second, I'm going to grab some water here. All right. Okay. All right, so a lot of that sounds confusing, right? What are these space-time curves? What does this mean? What's a geodesic? Who done it? What is this? Right? So all this is, to think about it in a less fancy way, is say you have an inertial observer represented by T and X here on the graph. So they're not moving, so they're not experiencing any deviation in time or space. And then we have an observer who's in a strong gravitational field or who's accelerating. And this is represented by the coordinates T prime and X prime. And you see here that there's an angle of deviation between them represented by phi. And what this is this is the amount of hyperbolic curvature that they are experiencing relative to one another. This is what is this angle here is what's represented by the gamma factor correction. This is length contraction and time dilation. So if you're moving at, relativistic speeds, you're going to experience length contraction and time dilation relative to those speeds. And the faster you go, the more you experience. Less fast, less you experience relative to an inertial observer. Okay, so hopefully that breaks everything down for that. And then we have the Lorentz transformation to solidify this in the mathematics. So a regular Galilean transformation to describe to describe velocity relative to relative observers would be transforming the distance, right? You would add their velocity and time so that you could figure out where they've moved to on the graph, right? So this is all this is doing here. And then when you do a Lorentz transform, what you're doing is you're taking the distance, right? And you're applying you're playing this right here to get how much you're contracting proportional to your velocity. And then you're also applying the same thing for time, because these things are going to be proportional such that you could transform in between, or back and forth to one another, and there's no discrepancies between them. And that's all based off of this right here. This is their gamma factor correction. The square root 1 minus the v squared over c squared. All right. So again, to reiterate the conception of the equivalence principle, which is put forward in the general theory to say that an acceleration is equivalent to being in a gravitational field. We have that represented by the rocket here, which is accelerating. And then we have your boy here dropping an apple. So we're saying that an effect of the apple falling would be the rocket going up. And then just normal gravity, right, would be the apple falling. And these are supposed to be equivalent. All right, so now we got some more bendy space-time conceptions for us to look at. Very nice. So here we see so when they talk about space-time and the fabric of space-time and all this, there's no fabric. That's the only fabric they have is a coordinate system, right? This is a graph. So if you can imagine this graph warping and bending, that's the fabric of space-time. It's just the bending and warping of the tool used to graph it out, right? It's not a physical. It has no physical meaning, right? Although we throughout the history of this theory and how they put it forward, they do canonize this as if there is a material substance and we'll get into all that. But to be clear, there's no fabric of space-time. It's a coordinate system, and the expression of it is done through contraction and dilation. All right, so these are Einstein's field equations here. Going from right to left, we have mass, energy, and momentum represented by T mu nu. And this conserves energy, momentum, any energy flux, anything like that into a gravitational field. The 8 pi g over c to the fourth is the distribution of the gravitational field. And what that's doing is you can think of it like a gravitational field would be like a density per cubic centimeter, and how much gravity can be in that cubic centimeter. And then as it's going out, like a gradient, right? So you can think of it like that. And then the lambda g mu nu over here is for the cosmological calculations that they do, where they invoke cold dark matter and dark energy and all that. So this gives additional curvature with respect to that. So most of the time when they do calculations, they just set this to 0 and this does nothing. And it's all about your boy g mu nu over here, which is a combination of a Ricci scalar or a Riemann tensor and an Einstein tensor. And basically what this is doing is this is describing how space-time, right? How that fabric, how the coordinate system is distorting, warping, right? Relative to the intensity of the gravitational field and the distance away from it. So that'll describe two bodies, their gravitational field and all that, and how space-time is warped in relation to that. Now, the cool thing about this is that you can swap out different tensors to get different results. And what they've done with that is when they get a result that doesn't match the relativistic predictions, they'll swap out another tensor so that they can get in, so that they could, control it a little better and rein it in, because these equations are nonlinear field equations that, go out to infinity. So to solve these, you have to make large approximations to linearize them and rein them in essentially to solve them. So that's what they do with the math there. And if you can't do it with the g mu nu, you throw in another one and see how that goes. All right. So we already went over that. So again, the T mu nu. So to kind of break down these indices here, the mu and the nu here are indices that describe the momentum, energy flux, density, all that stuff is contained in this matrix here. So when they extract all that out, that's what they're going to be getting into to actually solve these. All right. So what did we just learn? We learned that Newtonian dynamics of the solar system and is supposed to be the causal mechanisms of bodies in motion. They went to test that experimentally several times with the telescope and water through interferometry, and they got measurements that did not correspond to a confirmation of the heliocentric model in the Copernican principle, which is that the Earth is in motion. One second. All right, let's see. Now, we're going to get into some problems here. So we already touched a little bit on the interferometry, where Sagnac came along with his rotating interferometer, showed that there was an absolute space for something in uniform motion. So in the same respect, if you took Einstein's concept of taking a circle and expanding it to infinity so that it's linear, if you reduce that back down, that would be the Sagnac device, right? So it turns out there is an absolute space for that, and you would be able to measure Earth's velocity. So they have to present this new theory as an extension to that and swoop up any incongruities with that, right? So we're going to disregard the uniform motion of the rotating device, and then we're going to treat that strictly as acceleration so that we could, basically mathematically explain it. Okay, so let's see. Curvature, geodesics. Yeah, okay, we changed the orbits to geodesics so that there can be no question of an absolute reference frame for the motion. Or that's what's being proposed in the general theory. And then to piggyback off the back of that, they're going to use general relativity to explain the perihelion precession of Mercury to supersede the Newtonian explanation of the motion of the bodies. Okay. So real quick, before we get into the proofs of that and the measurements of the perihelion and such, we'll talk a little bit more on the tensor calculus stuff that they use for those tensors. So like I showed you the tensors and the indices. Now that's not just all abstract fake mathematics. It has practical application. You can use it for real things. An example of that would be, say you're an engineer and you have an I-beam and you need to describe the stress between this point of the I-beam and this point of the I-beam, and say, this side of the I-beam is going to be close to a heat source. So there's going to be some dynamic forces at play. There's going to be more stress here, et cetera, right? You could input all of that in the tensors and define the geometry of all this, of the I-beam and all that, and work that out. So it has, real practical application and all that. It's not just completely abstract, but what they're doing with the sky, they have to provide physical meaning with it, because in the lab, like on the Earth, we can test this I-beam. We can figure out if the coefficients we're applying to it, if what we're doing mathematically to it is actually representing its physical stress points, it's where it's going to break, where it's going to fail, et cetera, right? All right. Okay, so that's the end of the math section of it. Now we'll get into the measurements, right? So we're going to be looking at the perihelion precession here, and these are measurements that are done in arc seconds, as pretty much everything in the sky is done. So if you take a protractor, hold it up to the sky, and you divide your field of view into 180 degrees, if you took the distance between 1 and 2 degrees and broke that down into 60 sections, you would have 60 minutes of arc. And then if you broke each minute of arc into 60 seconds, you would have 60 seconds of arc per arc minute. And then so what you could do with that is you could break 1 degree into 1/3600th of a degree. And then they further continued the scale with high altitude observations with quote unquote satellites and planes and whatnot, where they say they can get into the milliarcs and micro arcs, which is 1/300 or 1/3,600,000th of a degree and 1/3,600,000,000th of a degree, allegedly. All right, now for optical viewing conditions. So remember, this was back in the day. This was pre high altitude, whatever milliarcs and whatnot. So we're down here in the arcs. So it says here from Mac Roberts from Sky and Telescope magazine in 1995, he says, viewed at the high power from the bottom of the ocean of air, a star is a living thing. It jumps, quivers, and ripples tirelessly, or swells into a steady ball of fuzz. Rare is the night at most sites where any telescope, no matter how large its aperture or perfect its optics, can resolve details finer than 1 arc second. More typically at ordinary locations is the 2 to 3 arc second seeing or worse. So we're going to get into some highly precise sky measurements, and the typical ordinary viewing conditions are 2 to 3 arc seconds, he's saying, and rare is the occasion where you could possibly see 1, and you definitely can't resolve anything lower than 1 from the ground. All right, so to kind of look at that, this is what it would look like actually. This is for another part of the presentation, but anyway, this is for gravitational lensing. Sorry, got a little thrown off. We'll come back to that one. Oops. One second. This is. Why is that playing? Oh, thank God. Sorry. That was playing in the background. I couldn't pause it. It was on autoplay. Okay. So we're going to look at, when we get into the gravitational redshift, we're going to need to know about the frequency shift in light. So to kind of talk about this, here's a video on the Doppler effect. Now we don't need to watch too much of it, but we'll go through the simple concepts. So the frequency shift in light or sound or anything is the apparent shift in the frequency of the wave relative to the motion of an observer in the source, or the relative motion between the observer and the source. So to kind of put that in perspective here, we have an observer lad here, stationary, and we have, dang it. 1 second. Okay. So we have, all right. We got stationary observer here, and we got car lad he's coming at, and so the sound wave that the car is emitting is going to be at a high pitch frequency because the sound waves are compressed as the source is moving closer to the observer. So you're going to hear that high to low sound. And then as the car gets farther away, the waves expand from each other, and they're not, as compressed because the source of the thing that's emitting it isn't moving towards it. So you get that low effect. So you go from high to low, right? So that effect is called the Doppler shift. Now, when you apply that to the frequency shift in light, they say that your relative motion will cause a frequency shift, and then they're taking observations of light where they're splitting it into a rainbow, and then looking at the frequency of colors produced, and based off of the intensity of the colors, they're saying, okay, well, XYZ must have happened to cause this frequency shift so that we're seeing this effect in the color spectrum of the starlight that we're splitting. So hopefully that makes sense to everyone. And to kind of put that in perspective here, we have a telescope looking at starlight. Starlight's going to come in, it's going to hit a collimator, so it gets focused into a nice, fine, cohesive beam, and then it's going to hit a dispersing element, and that's usually a diffraction grating, so it has like really fine slits, and it's just going to split the light beam and reflect it back and forth until until the other end of it will project out a rainbow, essentially. And then they're going to mark that down on photographic plates, and then they're going to determine the intensity of the colors and then tell stories about why certain colors are brighter than others. And that's how they determine the correctness of their theories, essentially, right? Okay, so for the proof of the general theory of relativity, there are three things that are put forward to give it physical meaning for the sky, right? Because this whole thing is about how do we give physical meaning to the sky through pure mathematics and give no actual lab experimentation that would confirm it. For example, right, like the interferometry not producing the velocity necessary to confirm heliocentrism, or water in the telescope where you would have to correct your the angle of the telescope to match Earth's velocity. So they gotta come up with some other creative ways to do it, and to kick things off, they're going to do it with pure observations of the sky, right? So we got the perihelion of Mercury, we got the deflection of light rays from a gravitational field, so gravitational lensing, and then we have gravitational redshift. Now, these all combined together are going to turn the fabric of space-time that doesn't exist. This is what's going to give it physical meaning, to actually change light, to change orbital paths, to have meaning. It has these three things have to be worked out, right? Essentially, is what they're putting forward. All right, let me switch back to the other one. Right. Gotcha. One second. So annoying. There we go. Now did it update properly? Cool. All right. So the perihelion precession of Mercury. So to get into what this is, for those who don't know, Mercury has a precession to its orbit, so it wobbles a little bit as it's going around the sun. So they're saying that they made observations over the course of 40 years. There was a guy named Urbain Le Verre who did 40 years of observations, and he projected out his observations to 100 years. And over the course of a century, the Mercury will precess by 1.25 degrees. So earlier we were talking about arc seconds, arc minutes. So over the course of a century, we'll get a full degree of precession out of it, or actually a little more, 1.25. So to explain this, now this is a real problem, because when a planet is in its perihelion, it's actually bound to gravity at the exact inverse square law. Like there's no room for, maybe there's a little gravitational drift or something. No, it's locked in hardcore. So if there's any deviation from that, it would mean that it's not caused by gravity and there's some other mechanism. They can't have that because they've committed to mass attracting mass as the mechanism. So as minuscule as this measurement sounds, right, and like a 1.5 arc seconds, who cares? What does it mean? Well, for them, it was, it's a deal breaker, because mechanically the explanation couldn't be gravity if this measurement is real, right? Because when they account for the inverse square law of gravity, how it drops off, right, and the perturbations of the other planets, right, they were left over with 43 arc seconds to explain, and they couldn't do that. So Einstein came through and he was like, hey boys, I got you with the space-time curvature. I can fully explain it. So using his mathematics, they came up with the full solution to the 1.25 degrees over the course of 100 years. So he solved that missing 43 arc seconds. Is what they say. Now, this is what's called a post-diction, right? These observations were already made, and then the math is being imposed on top of this to explain it. Now, Newton already had like Newton's equations applied, so they already had a framework where they were hard capped with how they could explain it. So they reached their limit on that, and then Einstein, having the benefit of knowing the observations and all that, he was able to adjust the math proportional to explain it. All right, so we'll get into the derivations for that now. So to explain this, we have Paul Gerber, who solved this in 1898 with his derivation, and this is the final formalization of it here. So we have psi equals 24 pi times alpha over tau squared times c squared 1 minus epsilon squared, right? So this, what they're doing here is they're describing that perihelion precession and the mechanism that Paul Gerber put forward here, this tau squared times c squared, is setting the gravitational speed limit to the speed of light. So we're all familiar now with the concept of a gravitational wave and whatnot. So this is how Gerber expressed that that there was like a delay in how gravity is propagating, and that delay over the course of 100 years would cause that precession. So that was his equation and derivation for it. Then Einstein comes along with the exact same equation, just changing the psi to an epsilon and then adjusting the tau to a t. And what Einstein does here is this is just the periodicity of Mercury's orbit squared. So instead of doing tau squared to set the speed limit for the speed of light, so it's basically him multiplying the speed of light twice to get his thing. And then Einstein just changes it to the periodicity of the event, and he gets the proportional ratio for the solution. Now, there were some additional problems with that, right? And obviously it was already derived by another person, and you can get into like these two equations are the same. They make, mathematically, but the story about this t is different. So it's like, how do we determine which one of these is true, right? Now, that's where we're going to have to get into some more experimental stuff. But, so this isn't really a good proof of anything for the theory itself. But this is how they did that. Now, another more substantive proof that they have is that they say that Schwarzschild derived his metric from Einstein's field equations and came up with a solution for the perihelion. And using his solution, where he treats the sun as a spherically symmetrical object with no charge potential and stationary, non-rotating, so it has no additional energy to cause any additional curvature to the space-time. And then you could use the static space-time metric, which is not time dependent. And then you can treat the orbital body, right? So you can treat Mercury as a photon traveling along a geodesic. So using a null geodesic path to describe the orbit. Dude, if there was ever a way to mathematically finesse an observation into a mathematical solution, this would be what you would do, because obviously the sun isn't perfectly symmetrical. It's got charge, et cetera, like even in their model, right? So this is just them imposing conditions to solve an equation, right? So earlier how I said the equations are nonlinear and you have to make broad approximations to linearize them and solve them. So this would be what that looks like. Okay, so does any of it have physical meaning? So far, we're still stuck in the kinematic stage, and now we're going to get into the more physical substance of the space-time mechanism to substantiate it. So this is going to be the deflection of light rays. All right, so we have the Earth here, we have the sun here, we have an apparent star location here that's been shifted to another apparent position. And this is due to the gravitational field of the sun. So we'll get into what all that means here in a second. But basically, using Newtonian mechanics to predict the deflection and Newton's concept of light and how gravity would interact with light, you're able to produce a prediction of 0.87 seconds of arc for displacement at the limb of the sun's gravitational field. I'm sorry. Yes, at the limb. Correct. And then for Einstein's theory, he says due to how he's calculating the expression of gravity and how it works and his concept of light, it's going to cause a deviation of 1.75 arc seconds at the solar limb. And then because it's an inverse proportional relationship, as you get further away, that angle is going to get really, really small, really, really quickly as you get more solar radii away from the sun. All right, so for simplicity's sake, we can just say that the two theories had different predictions for how they treated light and how gravity would interact with it. So here we have a little graph of the displacement angle over solar radii, right? So as you get further away from the sun, how much displacement there's going to be. So if you're 1 solar radii, you're going to get 1.75 seconds of arc. And then as you get out to like, say, 8 solar radii away from the sun, you're going to be at 0.02 seconds of arc. So, practically imperceptible, nothing you're ever going to be able to see or discern, right? Now, to test this theory, right, they had been making celestial observations for some time, but there was an eclipse that was coming up in May 29, 1919, where they planned to set out an expedition with Arthur Eddington and Cromlin, his boy. They were going to take observations of the eclipse and see if starlight was displaced in the Einsteinian sense or in the Newtonian sense. Now, there's some real ambiguity here with the observations, but we'll go over it anyway because the solution is it doesn't matter if these observations exist or not. They can be explained with constants in a proportional ratio, and again, we're left with kinematics. So to get more into that, we'll just go over the narrative here. So Arthur Eddington sets out to the west coast of Africa, to an island called Principe, and Eddington sets off to Sobral, Brazil. And they say that Cromlin's data was unusable due to thermal expansion and contraction during the eclipse, due to a temperature differential during the eclipse. And then Eddington's plates, all of those were unusable except for 2. And the only 2 that were, and his were unusable due to weather conditions and, other stuff. So he's just got his 2, and he has to take them back to England to have them analyzed with Frank Dyson Watson so that they can determine whether or not he measured Einsteinian shift in the displacement of starlight. So the boys get together 6 months later and have a Royal Society meeting, and they're like, yo, Eddington definitely measured Einstein's gravitational shift. Gravitational lensing. There was definitely displacement, blah, blah, blah. We're rolling it out with a successful confirmation of the theory. Here we go. Now, there was a couple people that gave pushback at the meeting, and we'll go over the biggest one here, which is presented by Dr. Silberstein, who's saying here, and I'll just read from the text here. It says, I believe the result to be essentially an isolated fact. There is a deflection of light rays, but it does not prove Einstein's theory. It cannot be logically deduced from his theory as a gravitational effect in the absence of the spectroscopic results. And the spectroscopic results that he's referring to is while there was an eclipse going on, there was also gravitational redshift observations being made. So earlier when we covered the telescope with the collimator and the diffraction grating and the photographic plate to measure the rainbow spectrum of light, right? There was supposed to be a specific spectrum shift. There was the light traveling through the gravitational field was supposed to be retarded such that it would produce a certain color when they split it into a rainbow. And if it doesn't have that specific color match to it, then they can't establish a cause and effect relationship to any displacement if there is any, right? It would be an entirely separate effect because the way that you can think about the gravitational effect. So think of light as a wave. It has to wave at a certain rate for you to see like a color spectrum or what have you, right? And as it's going through a medium, and you can think of the gravitational field as a medium, and based off of how close it is to the source of that gravitational field, the medium is going to be more dense. So as it's traveling through a more dense medium, the light waves become retarded. So that vibrational rate goes down, and so you're going to see a color shift essentially, right? So that's what they're saying here And this gravitational field would have to shift the light, because the gravitational field is also what's curving space-time to produce the deflection of the light ray itself, right? So these two things have to happen in tandem. Otherwise, no spaghetti or whatever. Now, this is a huge pushback for him, and we'll continue to read through here and read his thoughts on it. So he says, and as far as we know from St. John's and Evershade's observations, the predicted shift of the spectral lines of accounting of an amount exceeding almost 100 times the probable error of the modern spectroscope, as Professor Fowler has just told us, is not obtained. And then he goes on to say here that St. John purposely observed as many as 43 lines at the sun's center. So it's just basically like an accuracy check. He took observations at different locations, et cetera, at different angles, so that they could figure out the relationship here. And he's saying they got nothing. So then he goes on to say that if there's no gravitational redshift to back this up, Einstein's theory fails completely, because the coefficients defined by the G mu nu, like in that tensor, right, that describes all this and the curvature for space-time, would be unity. So there would be no curvature. And if there's no curvature, then there's no way to explain the orbits. So remember back when we were talking about the orbits, they changed it to a geodesic, where you're traveling straight through the curvature of space-time. So the curvature of space-time would be influenced by that gravitational field. And if there's no gravitational field, there's no space-time curvature. So you can see where he's going with this. And then he goes on to break down Einstein's derivation for the displacement here. So this is I minus 2m over c squared times r. And the r here is the radius of the sun. C squared is the speed of light. M would be the mass of the sun. And the I here would be a phi, and it would be like the angle, right? The angle of displacement relative to the center of the sun. Now, what we learned earlier about mass canceling out and not being actually relevant, this is proportional ratio stuff, but we'll get into that here in a second. But basically what he's pointing out here is that this ratio that he's using to derive the angle for the displacement reduces to no space-time curvature, and it has no ability to explain anything if there's no gravitational redshift to correspond to it. So he goes on to say that Einstein's theory does not only give such refinements for the planetary motion of the secular motion, but for the perihelion, and not even the ordinary Newtonian or Kepler motion. So no circles and no ellipses can be described from a geodesic if there's no space-time curvature. And he says that the theory stands or falls on the correctness of the results of Evershade and St. John, and it would be unscientific to attribute the deflection to the gravitational field and space-time curvature at this time without those. All right, so we'll come back to that in a little bit. We'll move on to the displacement. All right, so we got the sun. We got concentric circles going out from the sun, each corresponding to a solar radii away from the sun. And one solar radii is defined as the center of the sun all the way to the limb where the edge meets space. And then as you get further away, that inverse prediction is going to drop off. So the angle is going to get smaller and smaller and smaller as you get further away. So the observations that Eddington made at the time were only within, were at the solar limb. So there was people at the royal meeting were also pushing back a little bit, saying, hey, at the solar limb, there's an electric field, a magnetic field, there's plasma, there's an intense gradient. We don't know. There could be dust, like who knows, right? We got the corona, got all this stuff. Who knows what's at the limb? And without the frequency or without that redshift, that frequency shift, we can't attribute it, et cetera, right? And then, so to show what's happening here, earlier I said that this is just based off of proportional or constants in a ratio off of, the only value that's going to change here is the R, right? So the radius of what they say of what they're saying they're looking at. So a guy named Edward Dowdy Jr., a plasma cosmologist, came along, and if you treat the sun as a Gaussian surface, meaning the charge potential and the electric flux would be equidistantly distributed throughout the surface of the sphere, and then emanating out, it would replace the gravitational field with an electric field, essentially. And that would substitute the gravitational field in the same way. So the only thing that changes here, and the mass would change to the charge potential of the sun instead of it being mass. So just by changing the story so here we're in another situation where if you change the story about what this variable is, you have a completely different theory that explains it with the same exact math. So how do we know what the difference is? Is this a plasma electric field, electric universe situation? Or is this an empty vacuum gravitational field situation? We can't determine from these equations. Now, it should be noted real quick that there was an observation that was made in the 90s where someone said that at 8 solar radii, they made an observation of displacement. Now, that displacement would be 0.2 arc seconds. So as we showed earlier, you can't even resolve anything at that limit, because the maximum you could resolve at all, even on a perfect night, would be 1 arc second. And 0.2 arc seconds is well below 1 arc second, let alone 2 to 3. So that observation is made in tandem with other observational material. So it's referencing the Hipparchus data set, which is a parallax data set where they say they have a satellite or high altitude plane making observations in the sky. And what they do is they say that, they can get down to those micro and milliarcs for the precision, and they can know the actual locations of the stars. And then what that guy he took his observation, mapped it out, referenced that data set, and then, through statistical probability, determined that he had measured Einstein displacement 8 solar radii away from the sun. So not something that you could actually confirm with any degree of precision. It's just based off of your willingness to accept the model and what you're calculating. Because as stated, the causal mechanism could be swapped out just by changing the story of what R is, because this equation to predict it is the exact same as Einstein's. So the displacement angle, 4K m over c squared r, same thing. Constants and a ratio based off of the one variable that would change, right? So when they look out at objects that are further away in the sky, right, when they send us things like, what's that one thing called? Hubble, right? When they send us the Hubble stuff and you look at the gravitational lensing on that, well, we don't know how big those stars or anything in that screenshot is, but they can define the radius to be whatever they need it to be. And then that will give them their proportional angles where they can go, oh, look, this star right here that's next to this light is being gravitationally lensed, and it's literally all based off of this. It doesn't mean anything. It could literally be a Gaussian sphere if you treat it that way, and they would have no way to refute that. All right, so just to recap on that, another non-mutually exclusive proof that's put forward for evidence as mutually exclusive evidence for the theory, and we'll get into the redshift now, because this is what is supposed to actually add the substance to all of this and provide the actual mechanism for everything, right? What's going to cause a frequency shift in light. And this will be measured through the way that a gravitational field affects light will be measured through its frequency shift. Whew, okay, got that out. All right, here's one more on the telescope, collimator, diffraction grating, projection, photographic rainbow thing. So again, if the frequency is shifted more red, it'll be due to, the strength of the gravitational field. And if it's shifted less red, then they'd have no idea. Okay, so there's an excellent 40-page paper by John Ehrman and Clark Gilmore, where they go over the history of gravitational redshift. And for the early years of relativity theory, like up until the 40s, I think it was, really, they hadn't really even decided if redshift even had any physical meaning in general relativity, because of the approximations that had to be made to solve for these equations. They were like, does this even mean anything? Is this actual prediction, et cetera? Are we just playing around? So it took quite a while for them to come up with a cohesive agreement for them to, establish canonized lore around. But so we'll skip to the lab experiment that was done in the 60s when they all had something that they could agree on, and we'll see what we can come up with. So we have the Pound-Repke and Pound-Repke-Snyder experiment in 1960 and 1965, respectively, and they emitted energy of a specific frequency from the top of a tower and at the bottom. And what they were looking for was a specific shift in the frequency, or the detector that they were using would only accept energy of a certain frequency. So the energy that it was set to accept would be the energy, or would be the energy output that would happen if the energy was, if the frequency of it was shifted as it's interacting with the gravitational field, right? So as I was saying earlier, like the density of the field, it would get more retarded as you get closer to the source, because that's where the strength of the field is. So as the energy is traveling from the top of the tower to the bottom, we're seeing the detector is set to detect the frequency that would be shifted from that potential. Okay, so they say that they got a successful detection from 75 feet, or from 70 feet, and then they did another one in 65. We're at 75 feet, and they said they got another successful detection. Now, there's some problems here, though, because in their paper, in the first paper they released, it was titled "On the Apparent Weight of a Photon," and what they were implying there was that based off of the detection method used, they couldn't determine if the frequency shift of light was due to the gravitational field, or if the speed of light was actually traveling faster as it was going down, as if there was like a downward acceleration to the light and it was like gaining speed of a material object. Actually, that's exactly what they said. that the classical theory and the relativity theory made the same prediction, so they couldn't determine anything. So they did the experiment again in 1965 using gamma radiation, and the purpose for that was so that the electric and magnetic fields involved with the detectors and whatnot wouldn't cause any frequency shifts or anything like that. It would be neutral to those, wouldn't respond, and they could more isolate the effects of the gravitational field. And what they got for that was the exact same. So they got the same measurement and same determination. They were unable, using that method of detection, converting the energy into an electric signal to give them a pulse. They were not able to determine if that was due to the speed of light being the same and just the frequency changing and inversely proportional to the wavelength, or if the speed of light was changing. 1 second. Hang on. All right, let's see. Just making sure the audio is still good. Okay, the frequency shift, velocity. All right, so they were unable to, 1 second. Yep, so yeah, I got distracted. All right, so they were unable to make the determination in 65 as well, and they suggested that they should redo the experiment using atomic clocks at the top and bottom of the tower so that they could time when they sent the signal and when the signal was received, and that would give the definitive answer if is the speed of light changing or is it the frequency shift at a constant speed of light. All right, so this is the atomic clock shuffle because after this experiment, right, they never followed through, or no one's ever followed through with timing it in that way. And in more modern times, they use, more precise atomic clocks, et cetera, but they keep doing the same exact thing. So they'll have a clock at X altitude and one at Y one at Y altitude, one lower than the other one, essentially. And they'll look at the frequency shift and the corrections that are needed to be made. And they go, oh man, it must be due to the gravitational effect, even though we can't substantiate it in any meaningful way. But they just kept repeating that, and they use the more precise measurements of that as like a reification of the more precise, accurate measurements of the first thing that they tried to reify but couldn't do. Right. So any atomic clock gravitational redshift paper is all suffers from the same problem as the Pound-Repke experiment. It's not, because the atomic clock, the way that it functions, it's ionizing gas and microwaves to create an electric signal, which they're using for a pulse. They can't determine if the speed of light is changing or if the speed of light is the same with that apparatus. So what's a lad to do to determine the speed of light if we can't do it if nobody will do it with an atomic clock? Well, luckily we have vertical interferometry. So similarly to how Michelson-Morley did their interferometry experiment on the horizontal plane, if you do one on the vertical plane, you can measure a variance in the speed of light, and that produces a fringe. And the only thing that would produce a fringe like that is if the speed of light going up and down is different, is being measured differently, right? So that's the only way that could be, and measured differently with respect to absolute space, right? Because the apparatus, while rotating, is the same distance and length, and while it's stationary, it's the same distance and length. So these measurements are made with respect to absolute space, and there's the fringe patterns for them. So I'll play this. Hopefully, it's auto playing for me in the background. Yes, it is. Nice, cool. All right, so these were two lads on YouTube that did their vertical interferometry experiments. The first one was Gruma, and he got two fringe patterns on his, and then a guy on YouTube was like, "Hey, this is a mistake. You did it wrong. Let me do my iteration of the experiment and prove you wrong." And then you could watch the fringe in his video, and and his interpretation is that he did it wrong, that he himself did it wrong, and there was error, and he was going to do it again. So he puts out a second video, more refined version, claims there's no fringe, and you could literally watch the fringe in the video. So, again, so we got the displacement, and then we have this guy, Chris Machado, who came along and did his vertical interferometer experiment. And what do you know? It measured two fringes the same as everyone else is doing on the vertical plane. Now, another possible explanation for this redshift is relative motion through an electric or magnetic field. This is known as the Stark and Zeeman effect, respectively. And there's a link to a Ken Wheeler video where you could watch him use a ferrocell and a neodymium magnet and he just moves the ferrocell over the stationary magnet, and using that relative motion, he flips the polarity of the field, and you can see the red shift will switch the blue these poles will shift here. This one will be red shift and this one will be blue shift, and vice versa as he drags it across, going in opposite directions. So that's anyway, that's the Stark and Zeeman effect. So these are physical mechanisms for the retardation of light that already exist and aren't accounted for, especially on the cosmological scale. Up until recently, there was some articles saying that some stars' magnetic field change the frequency shift in light. And it's like, oh, well, you can't really say that because, well, I mean, you can, but it's going to conflict with all the other instances where you have electric and magnetic fields that you didn't account for, and you explicitly attributed all the effects to general relativity. That's a huge problem, right? But you can literally, you can measure these effects, yourself and see them, and you don't have to rely on like the hypotheticalness of space-time curvature or anything like that, right? So you have actual physical substances, physical mechanisms to change the frequency shift in light, not hypothetical constructs that have never been measured or measured in any meaningful way, rather. All right, so that concludes all of the major proofs that were put forward to tie everything together. So to keep everything going, Kepler, Newton, big G, gravity, mass attracting mass, turning it into a geodesic, warping space-time. You're now in a free fall based off of the curvature of space-time. To put all of that on the table, this is the backbone of the experiments for that. So the perihelion, the deflection, the gravitational shift. So even at the time it was derived, it wasn't even tenable to put any of this forward. It was all refutable, even by the people at the time. But they didn't have a choice. They had to move forward with it because the theory, the relativity had already failed to explain the situation with absolute space regarding linear motion. So the uniformly rotating Sagnac device, and then Newtonian dynamics was failing to explain the perihelion shift. That's huge if your belief system is bound to a fixed amount that Mercury can move in. You're going to have to do all this to keep it alive. So there's one more thing to touch on, and that is the quantization of light. So the interpretation of in relativity is that light behaves a specific way, and that's through the quantization of it. So they use an equation here, E equals hv, to represent that, or sometimes you'll see it as E equals h nu. So you'll see that v here on the slide on the left hand side, E equals h nu. So there's that. Now, to kind of break that down, what that means is that the h is the Planck's constant, so that's how much energy can exist over 1 second, like the quantization of how much energy can exist in one area over 1 second. And then the frequency is just the oscillation rate of light. So they say that light travels at approximately 300 million meters a second. So you can think about that like an oscillation rate of 300 million times a second instead, and same concept. So what they're saying here is that 3 million oscillation rate multiplied by Planck's constant gives you the quantization of light, where the light will be made up of little tiny, particles essentially. All right. Now, the problem with this though is that there's no time variable here. So if we remember back to instantaneous action at a distance and all that stuff, right, with the Newton's equations for gravity, well, there's no time variable there. So this actually leads to the wrong predictions in several cases. But to give an example here of one of those, to say that light propagates through empty space, right, it has to be quantized as little chunks of particles, right, essentially, because otherwise there's no way for it to be waving through. So this is part of the removal of the ether, this quantization of it. So it's super relevant. But to put this into perspective here, so this is also what carries the momentum of light through the vacuum, right? So we have this wave particle duality that's going through a vacuum, but how does it vacuum propagate? Well, the momentum of it is based off of this quantization here. And because there's no time variable here, the quantization of light would mean that the physicality of these particles, right, would actually be proportional to the length of the emission of the light itself. So if you had a photon that was oscillating at 3 hertz, right? So just forget 300 million oscillations a second, just 3 hertz, just 3 oscillations a second. The quantized particles in that would be 300 million meters long. It would be the distance from the Earth to the moon in the heliocentric model, right? That would be like the physical length of the quantization of the particle. Right now, obviously, there's no 300 million meter long particles, yet this equation still makes pretty decent predictions for certain things. So what's going on here? Well, it's just kinematics again, and the quantization as a little tiny particle actually means nothing, unfortunately, for the quantum lads and the vacuum propagating lads. So conclusion, relativity theory offers no insights into the causal mechanisms of the motion of the bodies in the sky. Neither did Newtonian dynamics, and neither did, well, I guess Kepler gave us the best and most honest explanation, is that he didn't know why they moved, and he thought that the sun was singing a heavenly song and everything moved in relation to the song. So that's a way better explanation than all of this, in my opinion. But it's kept in its most pure form, right? You don't have to do any, attribute causal mechanisms or anything like that. And I think that that's a better way to look at it, really, because after 150 years, man, they still haven't come up with a way to apply dynamics to the sky in any meaningful way. So this is just purely a reification of the original kinematics to describe everything and then impose it as dynamics. And, that's clearly failed experimentally. And space and time are absolute. These measurements are done with interferometry, right? Interferometry wouldn't make the measurements correctly if space and time were not absolute. And the speed of light, like any other wave, the speed of its propagation varies relative to the observer's velocity with a 1-to-1 ratio in V over C. All right, that's it for how math met reality. If anyone has any questions, comments, concerns, we can go back to anything and break it down. Thank you, sir. Yeah, yeah, it's important to see the whole story. And once you have what they're even trying to do with the math, that's the important part because it's like we have this nice package bundle and stories, but like where did it start? Why has it changed? What did it, where are we at now? And once you see what they've done with it, you can see it for what it is, and it was never anything more than kinematics in philosophy. None for year for years for year. It's a huge problem. It's a huge problem. And shout out to Dr. Silverstein for breaking it down in the middle of the room because that was a from a transcript of their meeting, right? So that dude was just live on the spot pulling a Witsit. Everyone showed up talking about relativity and just shut it down. And then they went ahead and went with it anyway because they didn't have a choice because like I was saying, the importance of everything that they were explaining, they had specific thresholds for that. Let's see, there's a Robert Hunt. Okay, yeah, it says there's a Robert Hunt in YouTube taunting you endlessly. He claims he wants to talk to you right now. Can we get him in here? Absolutely. Here's a link to the Discord. Yeah, sorry, I don't read or I don't read chat because if I read something, I get super distracted. When Shane sent me a message on Discord, it immediately ruined everything. So yeah, Robert Hunt, if you want to come in, there's a link in. You're free to come in. Oh, is it one of? Oh, gotcha. Oh, I mean, dude. Well, you know how I am with like people that are like that. Like I that is that. Yep. So, real quick, somebody said they can't hear Discord in the YouTube chat. Can you guys hear it now? I just switched over the audio thing. Let me know real quick if you can hear Discord. Somebody speak, please, in Discord. Nice, dude. Yeah, just do a live concert for me real quick while we figure out this audio thing. Now they still. No. All right, where are we at now? Hopefully it works. If not, that's a shame, but hopefully it's good. No, it's definitely not. Yeah, I can tell it's not. Dang it. I know. That's super unfortunate. Man, why is there.
Nah,
That's so weird. Wait, speak again?
I was like, dang, if Stone keeps going, I'm gonna have to keep going.
Now it's good. Now it's good. Now they can hear it. Dang. Okay, I heard something about an invitation, but I don't see any links. All right, Robert. Here you go. Now, be forewarned. Oh, that's from Rockfin, bro. It's not even from.
Yeah. What's the? Hey, how are you? How are you doing that? How are you pulling the Rockfin chat? What are you using?
Oh, I'll show you later. It's a program called Social Stream.
Also, so you can even do like RTMPs.
Yes, but we'll get into it after. There's some stipulations.
Okay, that's lit though. What was the effect again? Whenever you're talking about the electromagnetic retardation, you said a specific name.
Oh, the Stark and Zeeman effect. So the electromagnetic propagation through a magnetic field or a electric field will be retarded, proportional to the strength of the field.
Okay,
And that was discovered by Stark and Zeeman, respectively, in the early 1900s. Super early.
Okay, nice. Okay, so in the Stark effect is the electric field, Zeeman is the magnetic field.
Mm-hmm.
And both effects have different intensities between components. Blah blah blah.
Yep.
Nice. It's better than me just saying electromagnetic retardation to actually know the name of it. Why not? Kind of like the inertial plane.
Yeah. Yeah, absolutely. All right. So, are there any other questions before your boy, what's his name, gets here?
I don't know how this works. I see my.
It's working all right.
You hear me?
Mm-hmm.
Yeah, are you Robert?
That's me.
Oh, fabulous.
What's going on,
Shalom.
man? Let's just before. Can we keep it chill and normal and stuff?
Wait, absolutely. I'm chill. I see me standing under a telescope. That must be my icon.
Mm-hmm.
I see Alan's blank screen right now. So I guess that's where we're at.
Yep. You
It
just
says
need.
conclusion.
Yep.
Yeah.
Did you have some contentions or what?
Tensions is that you guys are nuts. You know, I will say this, Alan, you've got a far better grasp of general relativity than Austin, who pretends he does. This is a guy who couldn't tell you what the equivalence principle is. I feel like you understand it. There's really only two, you talk as if.
All right. Sorry. I couldn't find the pan
Bro,
button
is that
fast enough.
McTune or what?
Anyway.
Oopsie.
Anyway. All right. So let's see here. I think that wraps it up then.
Bro, I am over here doing homework with my headphones off. I just hear a voice so loud, and some dude just, oh, you know this so much better than Austin. Let me tell you. I click. Like, good job, dude. Good job.
He couldn't. I even tried. I knew he was gonna be like that, so I tried to help him.
Honestly, I let it go on for too long. I couldn't ban fast enough.
You know what's crazy, bro? Is like, bro, like when people do the whole insult thing now, I don't even. It doesn't even like slightly phase me. It's like expected, so it's all good. I don't care.
No,
I'm
me
a
neither.
little mystified at how that guy expects anybody to listen to him. That's amazing.
Yeah, but shout out to him, I guess, or whatever. All right, so we're gonna wrap it up here. Toby, close us out, brother.
Close us out
from the top of the key.
Oh, from the key, I'm getting the pre-dunk bumps. That field goal. Let's do number 30, Aether Round Table, number 32. And tomorrow night, either maybe a Schooling Globers, get on the Earth Awakenings Discord server if you want to be there for that, or if you want to be part of the open discussion over there. Also, if you want to join the Aether Cosmology Discord server, you can go to aethercosmology.com, click on the little Discord icon on the left side there. We tend to hang out there. That's where we do these presentations at. That's where we do our readings, and you can tune in for that on Thursday night. That'll be live streamed. We do live reading and research, so we'll be doing that this Thursday night. And then Friday, tune in for Flat Earth. So if you want to join the Aether and Proud and the Level Heads, and that usually goes into Stationary Saturdays. And that's on Twitter, X Spaces, but also we usually stream that as well. So thanks again for being here, and everyone take care.